Okay, we're going to try to do a little bit of section chapter 3. It goes through a review of exercises. So parent functions, they like to write lines this way. I like to write it in the y is equal to mxb format because then I can see that the slope of this line is minus 2 over 3. And then I'll also see that the y-intercept is plus 6. This way of writing it is a waste of time. This is also a rewrite, and the slope, which is very hard to see, is 3 over 4. Bring the 3x to the other side, divide by 4. And the y-intercept is 12. The y-intercept is not 12, and this is not plus 6. The y-intercept up here is actually plus 2, and this one is minus 3. This is a root graph, also called a radical function. Starts at 0, 0, moves to the right. All y and x values are above or equal to 0. This is a radical function that's been phase shifted to the 2 to the right. This is an upwards facing parabola that has a vertex of 0, minus 4. This is a downwards facing parabola that has 0, 9. You should be able to identify all that quite quickly, including the domain and range. Solve each equation here. So here they want you to expand, put everything on x on one side, then resolve, and sort of you should use reverse bed mass. First you want to distribute and get everything on terms you can solve, and then you want to get x all alone. This is something worth writing. A lot of people have troubles with this, so probably just do the intro skills here for this video. A lot of people have problems with these ones, and it's a shame because they're way easier than people realize. When you have something like that, you go, oh geez, I got to distribute these fractions and keep track of this fraction and keep track of that fraction and put everything on. Well, no, you don't. 3, 15, and 2 all go into the number 30. The rule of mathematics says whatever I do to the left side, I can do the right side. You just got to make sure you identify the left side and the right side. And now I'm going to multiply everything by 30 on both sides and make my life easier. What's 30 times 1? It's 30. Divided by 3, it's 10. But I also have to distribute through here. What's 30 times 2? It's 60. Divided by 5. Well, how about 30 divided by 5 first? 6 times 2, 12. On the right side, 30 divided by 2 is 15. Now it's quite easy to see and much easier to distribute. Add up all your x's, get your 3's to that side, isolate x by dividing by whatever it's being multiplied by, or multiplied by the reciprocal, which I like to say. It's solved. This one's the same. And you might say, well, no, it isn't. It's got t at the bottom. Oh, well. What's the common denominator between 2 and t? It's 2t. So we're going to multiply everything by this magical number called 2t, but I must do it to the right side as well. Clearly on the right side I'm left with 8t, because you can only multiply the numbers. On this side, 2t divided by t times 6, the t's cancel out, I'm left with 12. 12 all alone too. Then plus 2t times this t is 2t squared, divided by 2 is just t squared. So now I have 12 plus t squared is equal to t. Get everything on the one side, and you can easily discover the factors and solve. This is just factoring. This is just factoring. Sometimes you got to use a quadratic, and you might say that's not factoring. Yeah, once you take the x out of each term here, you're going to realize that x can be equal to 0, but you're also going to be left with a factorable x squared minus 8x plus 16. And that's simply minus 4, x minus 4 squared. So x can be plus 4 or 0 to solve this. This also has an x out. I think we just did this. This, you might say, oh, this one can't be solved. This one you factor by grouping. Look at the left term. What's in common to the two left terms? And they were nice to put them together like this. You can factor out 4t squared, and you're left with t plus 3. What if you factor minus 1 out of these two terms? You're left with t plus 3. What can I factor out of both these terms? T plus 3. what am I left with in a bracket? If I do that, 4t squared comes out of that one, minus 1. Now I have two factors. I just got to solve for this. So t is equal to minus 3 on this one. And this one, 4t squared is equal to 1. T squared is equal to a quarter. And therefore, t can be equal to plus a half when I square root both sides, or minus a half. Two answers, careful. So you got minus 3 plus half minus a half. That's still a factorable thing. So you're looking for the 4 times 8, 36, something that multiplies up to 36, but it adds up to minus 13. 3 and 12, no, closer. 6 and 6, close. 36, yeah, 36. So I'm going to do the factors of it. I got 18 and 2. I got 9 and 4. There we go. Dreaming. So it's minus 9 minus 4, and you got to do the grouping by common terms or slip slide. Just go with the grouping by, I forget what it's called. You take 13t and you divide it up into minus 9 and minus 4. But don't be fooled. This first term is simply a t to the squared. That is still going to square out fine. Okay, what about the other stuff? Oh, inequalities. I'm terrible at inequalities. Just awful. But we'll see generally how to solve it. And hopefully I still can. I doubt I will do well on this. Whenever you divide by a negative number, you have to switch the sign. And whenever you consider a negative option, you have to switch the sign. In this one, we don't have to switch the sign. We just have to solve for x. And we see that x must be bigger when I divide by 3, by bigger than 3, which means we draw a number line, and right where 3 is, we put a circle, and then we solid it like that. We could also do it like this in function notation. Rounded bracket means 3 is not included. Infinity is never included. And you can put a little plus infinity there too. And that tells you the range as well as that, or the domain as well as that. Next one looks a little harder. And that's because you got to use a little logic. These two numbers, what does bigger than 0 mean? It means positive. So you need this to be positive. This is going to be positive when these two things are positive, or when these two things are negative, which means that you can set it for x minus x times x minus 3 bigger than 0 and figure out which one's bigger than 0. But you also must set it for x minus 3 smaller than 0 to figure out which one's smaller than 0. So this one says, well, my x can be bigger than 0. Is the other one bigger than that? This says x must be bigger than 3. Clearly 3 is bigger than 0. So let's try like 2 and see what happens. If it's positive 2 and 2 here, this is positive, this is minus. So clearly this one's the best one. So right now we know that x must be bigger than 3. 4 works fine. Over here, when we solve, we get x is smaller than 0, or x is smaller than 3. Which one's smaller? 0. Let's test it out with 2. When 2 goes in there, well, we did that. So now we know that x must also be smaller than 0 in order for this to be both minus. So let's try minus 1. When this is minus 1, this is minus 4, and sure enough, that'll be ultimately what our... Always remember your main goal. This is just to test it. Okay. So that means we know that x must be bigger than 3 or smaller than 0. And we put it on a number guide like this. We mark that as 3, and we mark that as 0. The circle means it's not included. And if you're in doubt, you test it. Take a 1, put it in this equation. You get a 1 here and a minus here. So you can see that anything in between does not work. And anything outside does. Not too bad. I still think there's a better way to prove it. This is just testing your knowledge of rectangles in terms of, and circles, and you got to know your radius, surface area of a circle, and perimeter of a circle. So this perimeter, you just add that. That's times 4. For area, 20 times 20. For this one, it's 2 times 8 plus 2 times 12, or 8 plus 8 plus 6 plus 6. For area, 8 times 6. For this one, radius, for area, it's 2 pi r squared, so it's 749 pi. For circumference, it's going to be 2 times pi times r. So if that's the circumference, you need to find out what? Determine the area? Oh, determine the area of each figure. Okay. So when they give you the circumference here, we need to figure out its radius by taking that and dividing it by pi. So we're left with 12, and 2. We're left with 6. So the radius is 6. Now we do 6 pi r squared. So 6 squared, 36 pi is the area of that circle, because that's what they wanted us to figure out each time. So they're just kind of saying multiply. And they're giving us, oh, my bad, here they're giving me the perimeter. That's a square. So that means that that's the total perimeter, which means the area, the dimension of that is 5. So the area is 5 times 5, 25. So that one you just multiply. So my bad. Now they're doing the same thing here, and they're giving you the surface area here. And it's for a cylinder. And you might say, well, how do you figure out the surface area of a cylinder? Okay, well, imagine a cylinder. It actually has 2 circles at the top and the bottom. And then it has the joining points, right? That's a cylinder. Figuring out the volume is quite easy. It's the area of a circle times the height. So it's pi r squared. You got to get pi r, and you got to get height, times the height. Because then you're filling in the circle over and over again as you go down, and you fill up the whole thing. But surface area is actually more interesting. What's the surface area of a circle? Pi r squared. We just said that. But there's 2 of them. So that's 2 pi r squared. But how do we add up the surface area of this cylinder that goes around? Well, that, if you unravel, is a rectangle where this is still the height. And this happens to be the perimeter of the circle. So this length actually happens to be 2 times r times pi. So now you have the surface area is going to be height times that. So the surface actually is 2 r h pi. Add it to the other one, 2 pi r squared. That's the surface area. Surface area is actually more tricky to figure out. They're giving you 2 things and asking you to figure out the rest, which is fine. Or they give you out that and they're asking you to solve that, which is fine. You got to learn how to divide. Before even solving that, figure out the dimensions first and then plug it in. And then they give you out this and only this. So you got to divide everything by the radius that they give you in order to figure out the height. Once you figure out the height, the rest comes. Calculate total surface area for the cubes for the following area. Okay, so cube surface area, if you imagine a dice or die, I guess it's die, has 6 sides, 1 up on top, 1 on the bottom. 1, 2, 3, 4 all around. So that means you take this dimension and this dimension, x squared, times 6. That's the surface area. The volume is just x times x times x. The width times the length times the height. For a cube, those are all the same, x cubed. So you just follow this for whatever x they give you. Express each. Oh, this is sort of useful. Get back into your notation, your how to do things in interval notation. Okay. So this is saying bigger than x is bigger than 3. How do we say that? We put a circle bracket to say 3 is not included, comma, positive infinity, and infinity is never included as well. How do you say smaller or equal to 2? Well, the left side is negative infinity, it's never included, comma, but minus 2 is included, so we use a square bracket. So that's minus infinity all the way up to minus 2, which is the same way as saying is x is smaller or equal to minus 2. How do you say x is smaller than 0? Same thing except circle, negative infinity, 0, circle, because 0 is not included, etc. Oh, how do you do an interval like this? Well, you figure out, since x is in the middle of that, it's going to be minus 2. Is minus 2 included? No. Circle, comma, 8 is included. Okay, so 8, square bracket. That's saying all the way from minus 2 all the way to plus 8, and that's it. This is the same except circle. Then this, they're just asking you to go back to that. Just saying from 5 to positive infinity, 5 is not included, so it's x is bigger than 5. This is negative infinity all the way to 1, which 1 is included. X is smaller or equal to 1, etc., etc. That's just XER. This one here. This is minus 10 is included, so is 12. This is minus 2 and 3 not included. 2 is included, 20 is not. Graphing technology, Desmos. This is a parabola upwards facing with 0, minus 5 vertex. This is a parabola downwards facing. When I factor out x, I get x minus plus 10. When I factor out negative x. And that tells me that it is a, the two intercepts are at minus 10 and 0, which means the vertex is going to be at minus 5. I could plug it in and figure it out. It helps to always know what you're dealing with. This is also parabola, but the only thing I know is that 0, minus 82 is the y-intercept. I'd have to factor it. This tells me it's a absolute value shifted down by 1. This tells me I've got a sine curve that's stretched by 3 and raised by 2. So if this is a normal sine curve, it's stretched by 3, and the whole thing has been raised by 2. This was the old axis. The 2 brings up the new axis. Get back into it. This is a reflected in the x-axis cosine curve that's 2 stretched. The period finally is halved. That's what the 2 means. It's actually halved. And the whole thing is shifted down by 5. It's very important that you get into recognizing your things. This graph discusses an issue, and I'm going to cover it before I stop and go on to the problems. When we take a derivative, let's say we're dealing with distance over time. One thing we've done, just for ease of learning, is drawn it as if a ball is being thrown. Woo! Boom. And we've always sort of said, oh, here's a kid over here, and he throws the ball, and some other kid over here catches it. But that's not actually what this graph shows. That's just to help us learn. Most of these graphs, distance are over time, and here's distance here. So when we go left to right, we're measuring time, not the ball traveling a distance. If we were to actually look at it logically, what these things are measuring, we would take a ball and say it's going up and down, up and down. And that's what this thing is measuring. It's measuring a ball that's going up, captured, slowed down by gravity, and then accelerated downwards by gravity. Which is why right here, the distance, okay, I'm going to do one like that. If you look at the ball, how high it's changed in distance, it's only gone a little bit up. It's only gone a little bit up to here, and then a little bit back down. It hasn't traveled much at all. If we take this same square, though, and we go over here, look how much distance this one has traveled from here all the way down to there. That's why its acceleration, its velocity downwards, is much faster. So when we take a slope here, we get distance over time. And we've learned, because distance is the change in y and time is the change in x, we've learned that that's called a thing called the velocity. Well, we're going to go, which is usually meters per second. We're going to get into the second derivative where we take so the first derivative would tell us velocity. We're going to start taking second derivatives, which is the derivative of the velocity, and we're going to get into something called acceleration. So if the first one is meters per second, or first one is just meters by seconds, and the first derivative is meters per second, the third derivative is meters per second per second. It's showing us how much that velocity is changing every second. And this we call acceleration, and this is always meters per second squared. That's where that comes from. It's meters per second per second. Both just measure a rate of change. Acceleration measures the rate of change of velocity. Velocity measures the rate of change of distance. And acceleration, you can even say, well, we can measure the rate of change of distance over time, but it's going to be a different value. When we take a derivative of this one, we're really getting a measurement of the change of this one, not of that one. That's a big thing that this chapter covers. Another big thing that they want to go over is when we think of about a pendulum, we usually take this middle part as ground zero. In other words, how far it's traveled from here. When the pendulum swings out max here, we use this distance to sort of say to the left. And we use the other side to sort of say to the right as the pendulum swings. But when we graph that, when we graph it, we're using a sine curve. I'll just bring that up. And when we start the sine curve, let's say to the left, we'll just start it to the left. That's the green part. Then it comes back to middle. This is where it started. Suddenly, it travels the path that I've drawn up in red and repeats over and over again. So you can see that this green part represents this distance away from center, and this red part has swung to the other side and represents this distance to center. Now the x-axis represents the middle point here. So you have to understand now that these graphs represent either left or right of center, or in the case of balls, the ball goes up, it goes down, or a car, let's say car goes this way, comes back, goes past, it's the distance up or down from home. This fact that it's curved this way is just a visual representation of time. It really shouldn't be shown to show something being thrown from one person to another. Then they're going to get into the notion that not only when I have a graph and I find the derivative of that graph, when I set that to 0, we learn that that means the tangent, the slope of that tangent is 0, measures a flat spot. That's going to be really useful. The second derivative is going to tell us a lot of stuff too. It's going to tell us a really cool one called the inflection point. And that's key to know, inflection point. We're also going to learn how to use the second derivative to easily spot a maximum and a minimum on a multiple curve graph, because that's going to be useful too. Because you're not always going to have the visual. You're going to have only the data. What's an inflection point? I might as well sort of cover. Imagine you're going down a toboggan hill. Going down, 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 steep, steep, and curve back. Okay. Imagine a sled here. Not much fun here, is it? No. A little bit more fun here. A little bit more fun here. Tons of fun right there. Oh, we're going back to the less still fun, but not as fun. Now we're going back to red, and then we're ending the way we started. Sort of fun, but I wish the ride was continued. It's clear that we get faster, faster, fastest here, and then slower and slower and slower from the fastest point. This change in direction is called an inflection point, and it's when we go from a steeper slope to a less steeper slope. It's essentially when the slope has decided to change directions and go the other way. And when we have a second derivative that's equal to 0, it tells us exactly where that's going to happen. Very useful, and you'll see why. Anyway, they train you into showing and understanding why, what motion is and what the measurements mean, and where we can figure out when it's going to the left and when we're going to the right. For instance, if I have a cubic that represents something going a distance, I can see it's going away. And let's say that this is home. It's going away from me here, came back home there, it's traveling the other way and going back. If I take a derivative of this, I might end up with something like this. And it's going to tell me, actually will probably be more accurately like, I don't know if it'll be like that. No, actually it'll be like this. And this will tell me when its velocity is negative and when its velocity is positive. When is velocity negative? When it's going down the slope. When is velocity positive? When it's going up the slope. When is velocity 0? At the peak of the slope, right? So I actually should have taken this there. And this is unlikely to be a parabola derivative. The second derivative will often be a line, at least for velocity, accelerating, whatever, and this will show you the constant acceleration. In other words, how that speed is constantly changing. If that's not a line, then the speed is not constantly changing. It's changing even faster. You can imagine that in car commercials when they go from 0 to 60 in 5 seconds. They're saying that this car goes from 0 to 60, so it goes 60 kilometers an hour in 5 seconds. So that's really 12 kilometers per hour per second, which means that velocity is increasing 12 kilometers per hour every second as you hit the gas. And that's what acceleration is. It's dramatically increasing from 0 to speed. And this is just going to teach you to read the graphs and analyzing motion with gravity. You can just discover that 10 meters per second squared is an important value, and this is mostly to help you in physics. And then, so I'll start 3.1 next time.